I've been using ASAP since 1988, and it plays a central role in almost everything that I do. Much of my work is straight light analysis, and ASAP is perhaps one of the most powerful tools that I know of for doing straight light calculations, finding straight light problems, and perhaps most importantly, identifying where the straight light is coming from. I've also used ASAP for a good many other projects. I've used it for doing telecommunication systems, analyzing wave optics performance in particular. ASAP is extremely powerful and extremely flexible in its ability to propagate light not just geometrically, but wave optically through the very same models. We don't have to construct one model for geometry and one model for wave optical analysis. It's well known that ASAP is able to perform geometrical optics calculations. In particular, ASAP is widely used in the illumination field to calculate realistic representations of both sources and optical systems. Somewhat less well known is that ASAP is also able to do wave optics or physical optics calculations, modeling the effects of diffraction as we propagate through optical systems, or the effects of spreading and propagation and interference of laser beams in optical systems. These calculations are done by a relatively unknown algorithm called Gaussian decomposition, which I'd like to summarize and discuss now, and then prepare and show a very short demonstration. The slide that you see here represents the essence of Gaussian decomposition in 2 dimensions. We have an initial field, which is not a Gaussian, but rather, in this case, something close to a flat top. And we'd like to propagate that flat top through a couple of lenses to a focal plane and calculate the irradiance distribution at that focal plane, using all of the wave optics formalisms that we've come to know and love. The essential idea is that an arbitrary field, in this case our flat top, can be broken up into a coherent summation or series of Gaussian beams. The advantage of Gaussian beams is that they remain Gaussian as they propagate through the system. That is to say, a Gaussian beam retains its Gaussian form, and indeed we know how to propagate Gaussians through optical system as long as the local area that each Gaussian propagates through is not too strongly curved. Therefore, we take each of these Gaussian beamlets, we propagate each of them individually to some arbitrary plane, in this case an intermediate location, and because we know how to propagate Gaussians, we know how they behave through optical systems, and because Maxwell's equations are linear, or the wave equation is linear, we can superpose those Gaussians at this intermediate location to calculate the field there. Indeed, we can go all the way to the focal plane, where the individual Gaussians overlap, to calculate the point spread function at the focal plane itself. Now, in order for this to work properly, we have to have an efficient and dependable way to propagate Gaussians. How do we do that within ASAP? It turns out that there is a one-to-one mathematical relationship between propagating Gaussians and tracing rays. That is to say, if I can trace rays through my optical system, I can also propagate Gaussians. The slide you see here conveys the essence of that idea. We represent the position and direction of the Gaussian by a single ray called a base ray, essentially going through the peak of that Gaussian beam. We have another ray, so-called waist ray, that determines the size of the beam, and a third ray, a divergence ray, that represents the divergence of that beam. Now in practice, this is only a 2-dimensional figure. We would actually require at least 2 more additional rays in and out of plane so as to be able to model the performance of the Gaussians in both dimensions of our system. In practice, we call the base ray, but we call the other rays parabasal rays. Now, as these parabasal rays go through our system, they get all mixed up. That is to say, what was the waist ray and what was the divergence ray gets mixed together in some very complicated way. It turns out, nevertheless, that there are mathematical descriptions that allow us to combine these rays together at any plane to tell us what the actual Gaussian is doing. The actual identification of a waist and divergence ray is not necessary. We don't have to keep that particular idea constant throughout our system. ASAP, therefore, propagates both the base ray and the parabasal rays using the laws of geometrical optics, doing the mathematical recombination at any plane in our system so that ASAP can tell itself how the actual Gaussian is performing. We then go to some arbitrary plane, sum the individual Gaussian beamlets together coherently to calculate what the total field should look like. Now, why would we want to use this algorithm? It turns out there are some very real benefits associated with Gaussian decomposition. First of all, conceptually, if not mathematically, it's easy. There's no matrix propagators, there are no complex differential equations, there are no Fourier transforms to do, no complicated math. It's just, at least conceptually, ray tracing, something that users can understand and something that can be done within ASAP using the existing geometrical optics ray tracing capabilities. Secondly, all of the non-sequential propagation ideas and methodology associated with ASAP carry over directly into our fully three-dimensional wave optics calculation. Because we're just tracing rays, everything that we do with tracing rays can be duplicated in wave optics. We don't have to tell ASAP what order the optical components come in. ASAP knows what order they come in because it's tracing rays through the optical system. Third, fields can be calculated anywhere. We're not limited to just object and image planes. We're not limited to just Fourier transform planes. We can stop at any intermediate location and calculate the irradiance or the phase or any other optical property there. Fourth, beam splitting and beam recombination, as is done in interferometers, is automatically contained in this unified formalism. As we propagate through our optical system, ASAP will simply split the rays at appropriate interfaces into reflected and transmitted components, and when we bring those rays together at some focal plane, ASAP will do the wave optics calculation, including all of the phase effects, to calculate illumination and irradiance and interference effects. Finally, if we include polarization with our Gaussian beamlets, all of the polarization effects associated with light can also be included inside this formalism. And so using this relatively simple idea of Gaussian decomposition and the ASAP non-sequential ray tracing engine, along with ASAP's knowledge of how to take this geometrical information from the rays and reconstruct Gaussian beams, we can do wave optics through any system that we can propagate geometrical optics through. Let's do a simple demonstration. What I'd like to do is a tracing of rays off a simple spherical mirror coming to focus and calculating the irradiance distribution. Let's start by doing that in a geometrical sense. Let's open up an editor within ASAP and begin defining the system inside ASAP. We first of all have to define units. We'll say units centimeters. We're then going to define our mirror, surface, optical. We'll place our mirror at z equal 10, give it a radius of curvature of -20. That places the focus at the origin, and we'll assume an elliptical aperture for this mirror with a semi-diameter of 2. We'll make an object out of it. We'll give it a name. We'll call it mirror, just to be original, and assign an interface. Interface 1 means the mirror is 100% reflective. Now we have to define a collimated source. Grid, elliptic, we'll place the source at z equals 0, give it a semi-diameter of 1, so we're going from -1 to 1 in x, -1 to 1 in y, and just for an example, we'll have a 25 by 25 grid of rays. We're going parallel to the z-axis, source direction, x component of 0, y component of 0, z component of 1. We're going to set up a window in the usual way. A rectangular window with the vertical axis being y and the horizontal axis being z. Profile, overlay, trace, plot. Okay, go ahead and do this. Execute. Here's our ray trace inside ASAP. We zoom in here, we see our collimated rays coming up to the mirror, shown in green, reflecting off of the mirror, coming back down, and coming to focus. Simple geometrical optics calculation. Now we want to turn this into a wave optics calculation. How do we do that? Clearly, the first thing we have to do is we have to define a wavelength. Wavelength, 550 nanometers. One command. We now want to turn this into a wave optics calculation. We do this by telling ASAP that we want to include not only the base rays, which represent the geometrical information, but also the parabasal rays, which give us the wave optics information associated with the Gaussian beamlets. We say parabasal 4, which says give me 2 rays in the plane of incidence and 2 rays out of the plane of incidence. Width 1.6 represents the Gaussian overlap from one Gaussian to the other. All right, we're ready to go. We execute the file. We find that we don't see much difference here. It looks exactly as it did before because we're tracing only the base rays graphically, but in fact ASAP is also tracing the parabasal rays in the background. To find out, we can do a wave optics calculation. We tell ASAP to move the rays to the plane z equals 0, which is where our nominal paraxial focus is. We set up a window yx, which is normal to our direction of our rays. I happen to know that this window will be too large by default, so I tell ASAP to bring it down, set up a resolution, and instead of doing something like a spot command, spot's position, to show me the geometrical spot diagram, I issue a wave optics command, which is spread normal. Give me this point spread function. ASAP calculates the function, writes it to a file. I use the display command to read the file and an isometric command to actually get a distribution. And here is my distribution, my wave optics distribution at the focal plane. We see it's not a perfect spot diagram, but rather has the rings that we associate with doing wave optics calculations inside ASAP. Now, this is a relatively simple example. We can do much more complicated examples. Let's take a look. Here's something I call a confocal unstable resonator. We have rays that have bounced back and forth between the mirrors, come off of the mirrors, and then propagate forward through the system. And in the process of propagating out of our resonator, we are going to impose upon our nice clean plane wave from our laser beam a central obscuration, some spiders, and an aperture. If we do a wave optics calculation in ASAP, these are the irradiance distribution that ASAP shows us. Near the resonator, we see something that looks relatively geometrical-like, a nice plane wave, or a plane irradiance distribution, with the cuts or shadows imposed by the central obscuration, aperture, and spiders. But as we propagate further downstream, the wave optics calculation portions of this become very apparent. We start to see ringing and diffraction rings around the struts, and we see even the Poisson spot, or the spot of Arago, sitting inside the central obscuration. When we get to the far field, we have something that's much closer to our more classic airy disk sort of behavior. Here's another example, more complex. This is a laser system, or a laser printing system, which represents the full non-sequential capabilities of ASAP for doing wave optics propagation. We have a diode laser source illuminating an aperture, reflecting from a fold mirror, going through a collimating lens off of a scan wheel, which then brings us back through that same collimating lens to a drum where we write information on the laser printer. What we find here is that ASAP does its normal non-sequential propagation for the light, but because we're doing wave optics, when we actually look at the irradiance distribution on the drum, using the method that we saw for our simple mirror example, we get something very complicated. Our point spread function is not a simple point or even a simple spot diagram, but rather a representation that includes diffraction rings around the focus. We can even do interferometers. ASAP sends rays in. We do beam splitting at the beam splitter in the usual way. Rays propagate through, are recombined when they come through the beam splitter, and then come to some detector plane. It turns out that one of these mirrors is deformed, and therefore we get interference between the two plane waves. And we can calculate the irradiance distribution of their interferometer, showing things like spherical aberration or astigmatism using this formalism. Here's a very complicated example of a ball lens. We're going to take our light, come down through our optical system, and then focus on the actual fiber through which we'd like to couple. ASAP is not limited in the plane that it can do wave optics calculation. What we see here is a wave optics calculation in the plane of propagation. That is to say, we have a plane that divides this total system in half, and we calculate the irradiance distribution all the way through focus in order to see what the irradiance or fluence looks like as a function of both longitudinal direction and transverse direction. In summary, we find that the Gaussian decomposition algorithm is a very capable algorithm able to work in ASAP's three-dimensional coordinate system to give us wave optics calculations through almost any imaginable geometry without the overhead or mathematics associated with some of the more complicated methods that are often used in wave optics codes.